Hello, and welcome to this video where I'll go through the exam from 2023. For the first problem, I'll sort of solve it in the video, and the two others I'll just go through and talk about them, about how the problem works and sort of how it's supposed to look like. I've cheated a little bit with the first problem and written some code, but let's start by actually looking at the problem. So it's initially it's called optimal taxation with government consumption. Initially, it's just a worker problem. So we have a worker that have to choose how many hours they want to work in a given day. They have between 0 and 24 hours, and they want to maximize utility. They get utility from consumption of market goods, consumption of government goods, and sort of labor. This utility from labor, and they have this budget constraint that sort of they can spend all that they earn in the market minus some tax. Then they have a free private consumption component. I guess you can see this as a utility thing, that even if they buy no market goods, it's the same as putting kappa in here. You can also see it as free universal basic income or something. It's not really important. We have this maximization problems. They maximize utility subject to the fact, or they choose how many hours they should work subject to the fact that they don't like working, but they like consuming goods that they can buy after they worked. Then there are all these parameters that have some restrictions, and these parameters were sort of set in their value. Then we're first asked to verify that the optimal labor supply choice is something analytical and for different values of G. One thing to notice here is that this analytical solution does not depend on G. So I've cheated a bit and prepped a py file for the government model. And it has parameters, and it has a solution for the Cobb-Douglas version, and there will be a CES version in a later problem, so it also has a separate solution namespace for that. That sort of, we'll get to that. And then it just allocates all the parameters, and then I've already written out these functions. So I've written out this function where I sort of say, okay, I know what C is, and it's a function of what's the utility for a given amount of work and a given amount of government spending. And I know what C is, so I don't need to sort of have that as an input. I can just calculate it with the budget restriction. I bound these. This is not strictly necessary, but you get into issues if either of these is 0, then you're taking log of 0, which is not nice. So it's nice to sort of bound them to be something close to 0, which is close to minus infinity. So it's not going to be something that's chosen necessarily. And this is just this expression, and the next function is just this expression written out. And now we want to verify that the optimal labor supply choice is given by this expression. We'll skip that. This is a later utility function. Plot utility. So basically, there are multiple ways to go about it. You can just optimize this over L for the two G's and show that, and that sort of shows what the solution is. You can also show more visually that the analytical solution is the correct one, and you can also show sort of the overlap with the visual and the numerical solution. Plot utility as a function of labor supply. Yes, so ChatGPT is sort of suggested to do something. Let's see if it's not quite correct, but it actually is helpful. So we want to do it for different versions of G, but we can sort of make a new vector. If we have a linspace of L, then this function allows us to put in an array, and it will sort of return an array for each L. think this looks good. Yeah, that's fine. So we plot this, and then we of course want to put the CP. We want to put the analytical solution on top. There's some errors in this code. It's fine now. So we plot the utility, and now we want to put in the analytical solution. Yes, and that's just calculated here, sort of given very directly. Yeah. Then we put that in. Guess we'll put it in here. We'll put a vertical line, XV line. Yeah. That should be something. Okay, and that looks correct, but it's helpful to zoom in a bit. And we can see we're sort of right on the money. This is the maximum of that function. We could also add, sort of to make sure, a numerical solution. And then I would just add it as a function so we can refer to it later. Define L star miracle self.g. And this function will be useful because there's a later question where we change the utility function. So it'll be useful to sort of have it for different utility functions. Func equals, and then we'll start with the C Cobb-Douglas version. I don't know why there are two here. Should only be Cobb-Douglas. Yeah. Par equals par. And now we want to access, so we want to allow it to have different utility functions. This will be relevant later. So we want to only get the attribute related to this. So in the beginning, I had two simple namespace, one for Cobb-Douglas and one for CES. And then we want to store the solution in that solution namespace. Find objective function, and now we want to get we want to actually only take out the correct utility function. So basically what this does is it gets the attribute from self called u plus ufunc. So when ufunc is CB, then it will call this function uCB, and if you write CES, it will call uCES. And now we want to do a numerical optimization of that problem. Start, we'll also put g equal 1 here. Optimize numerical. We actually want it to be bounded because we know it will be bounded between 0 and 24. Yes. I will put in ufunc here as well, so we can sort of call this function for different utility functions. And then we only want to calculate this one. We'll plot it either way. That's not important. So we have the numerical solution. Now we want to add this as well. And then we don't want this line to be dotted because then we can't see both lines. And let's see if they overlap. That's bounded. Bounce. Yes, nice. And we also want a legend. And we could add utility. That's not really the main thing here. Now we sort of show that it's the max of the utility function. We can also show it for g equals to 2. And it works just as well. Sort of the level of utility changes, but the optimal solution does not change. It's the same place. So this maximization problem, sort of the correct L, is independent of G. And we're going to use that later. Now we want to illustrate how L starts depends on W. And sort of we can get Python to help now. Copilot to help us with that. I hope, yes. So that's basically just calculating the analytical expression over different values of the wage, and then plotting that. So that's what's happening here. That's not what's happening here. So apparently it does it across different values of G instead. We can have the wage, for some values. For these sort of assignments, if you're allowed to choose your own values, then you just sort of look at the problem. What's the initial value? That should, of course, be included. And then some area around that. Let's do 0.5 to 3. And then you can sort of make changes as you go along. Wait. Okay, now we can calculate. And we only want the analytical solution, actually, because that was what we were asked about, even though it's the same. Curved plot. Yeah, this is wrong. So we don't want to do it for different values of G, because we know G is going to be the same always. We just put it like this. We don't want to do it for different utility functions, because we're just doing it with the analytical solution. And what we want to change here is we want to change V, W. And yeah, Copilot is telling me how to do that is I actually got to change the parameter namespace. So if you go to the analytical solution, it sort of just references W from the par symbol namespace. So we want to change that in each iteration. And then we want to reset it as well, so we don't changing it for the next assignment. Here, and then we just reset. Okay. We don't want to do this. Solutionation. L star analytical is not. That's right here. Simple namespace. Oh, yeah. Cool. Okay, and it looks sort of intuitive that for higher wage, optimal labor supply is also higher. but it filters out a bit, which makes sense because the utility function sort of has decreasing marginal utility. Yes, so now we are asked to consider a government who chooses the tax rate and spend all the taxes on government consumption, such that total government consumption is sort of what they make in taxes. So this tau times W times optimal labor supply for a given tax rate. This is why it was written kind of strangely up here, sort of to make very clear that optimal labor supply is a function of effective or post-tax wages, which means tau sort of enters directly in that expression. Yeah, so we need to input this locally. We don't have sort of we will get that later, but we don't have a real optimization problem here because L star is independent of G. So for a given tax rate, we can sort of calculate L star and then calculate G and then plot that into the worker utility.
And you'll see in the next problem that sort of if L star had depended on G, then it becomes an entirely different beast to solve. Yeah, but we can do it the kind of easy way. So we just need to, yes, do this. So plot L star across tau, not just L star. And we'll only do it for the Dosler's function, because as I said, it's something differently, quite different in the next model or the next version of the model. Yeah, so we need to sort of basically just have a grid of tau values. We'll just put that between 0 and 1 because it's the tax rate and it's sort of its range. And then we will, for a given tax rate and all the other parameter values, then we can calculate L star. That allows us to calculate G, and using both G and L star allows us to calculate the actual level of utility. Because although we can solve this problem without knowing G for the Coploftus case, or yeah, this problem, then we can't calculate the level of utility without knowing G because it's still in the function. So we create a tau grid from something. This could be 0. We'll say this 0.9 just to not make it that you don't have any income at all, because then you of course not work at all. No, plot. We also want to plot G star down to the problem. Yeah. And we want to plot U. Call it U. I dot tau. And now we just loop over the taus. And then we set tau. Then we just use the analytical function to calculate L star. And that takes a G, even though it's not dependent on G. Yeah, that's fine. That's this one. But yeah, it doesn't, so G doesn't really matter here. But we'll still feed it G, even though it's not necessary. Then we can put in the L star for the given tau. G should not be here. We should not have this G. And then we calculate G. So that was the tau times W times the, so coming from this equation, times labor. And then we can calculate the utility level. Another thing we want to do here is sort of save the original tau before going into this loop, because we're changing the par simple namespace, and we'll just reset it afterwards. Set tau. Okay, so now we've filled up these values. Now we want to create a figure. and then we just plot it. And this is something that Copilot is really good at guessing. We also want to do the next one, and it can sort of guess from what we have calculated what we're trying to do. I don't think we don't need to set grid because that's already there. Sometimes you gotta help it a bit. Utility, type utility. I mean, in an exam situation, you might spend more time sort of thinking about what you want your graphs to look like. But for now, I just do it the fastest way possible. One thing you can do is the tight layout thing, where you sort of, it often helps make these multiple axis figures a little nicer. Yeah, gives them more space. Okay, so we can see a higher tau gives lower labor supply. That makes sense. You have to pay more taxes on your income, so you work less. It gives higher government spending until the very end, where it sort of starts decreasing, which also makes sense. So this is basically like a can't remember the name now, but the tax thing where you sort of the higher tax rate you go, your revenue increases, but at some point it starts dropping because people will stop working entirely. Yeah, and you can see that utility, so this is very squished because utility is very low when taxes are zero because government spending goes towards zero. And in this, when you take log of something that goes towards zero, it becomes minus infinity. So we can maybe change the grid a bit and say it should look like this. This wrong one. And then you can see that utility is actually maximized somewhere in between because we have an agent that likes government spending and it can substitute it with their own private spending. Yeah, and now we have to find the socially optimal tax rate. So this is maximizing this utility function, and we sort of have it here already. Yeah, maybe we should actually, so now we sort of asked to maximize this, and we sort of, it's basically, we want to maximize a function that outputs this value. So we might as well make a function that creates that value. What do it? Define. My naming could be better with this. So utility star. And we just want to say given sort of like given that the budget is balanced. Yeah, we don't do it. We just do it in the only for conductors because there will be some changes, a lot of changes. So CP. And that's also how I would do it if I was doing the assignment. I wouldn't think that far ahead. So first we need to calculate. It's also easy to show a bit more directly. Yeah. And we also solve the labor problem. I'll start with. And here G doesn't matter, so we won't input it. G. Yeah. And now we can just call, we'll do like this. So now I've created a function called utility. I'll call it utility budget, actually. So this calculates utility for the subductor function for a given tau, basically assuming that the agent acts optimally and that the government balances its budgets, and then it sort of so it both calculates L star. This should be an analytical one. I think that was what it was called. Analytical, yes. All right. And then it calculates utility and it saves everything in this solution namespace. So now in this loop, we can just call health.utility budget CB, and then we don't have to calculate all these things every time. We can just pick them out, basically. G what's the called it? U star. Don't want to spend too long time naming stuff in this video. Okay, so now that we have the function, it's a bit easier to set up the maximization problem. So I'll create a new function called tau star. So Copilot sort of thinks it knows what we're doing, but it doesn't. Yeah, no. But we can use the comments. Computer optimal tag. So now we want the object function to be something that takes tau and returns the utility, given that you sort of have optimal behavior and balanced budget, and yeah, the utility comes from that, and that comes out of this one function. So we just need to set the parameter namespace to the new tau, calculate utility, and return sort.u star. And then we can just optimize. Yes, this looks good. Then we'll see what we get, and we can sort of visually see that we should get something slightly above a half. This should get and then we can see we get something that makes sense. Passive. Why is it doing that? This one is wrong. So we should maybe also have tested that we can recalculate this after we change the code for the plotting. All right, so now this works. I guess this should work. And we get that it wants 0, which does not make sense. Because we just saw that should of course return minus because we're minimizing. Yes, something slightly above half. Yeah, so we have this problem. First of solving a consumer problem, and we sort of see we have a nice analytical solution. Then we're asked to assume that for a given town, the government will balance its budget, and sort of, because we know L star does not depend on G, then we can just solve for L star first for a given town, calculate G, and sort of calculate collective utility afterwards and maximize that function. Now we're given a new problem, which is similar to the one from before, but a bit more daunting, looks more scary, and it actually is. Yeah, so the thing that makes it more scary is that now the solution will depend on G. This formula is also scary, that's why I wrote it up before starting this video, to make sure there weren't any mistakes in it. But it's basically, it's similar to before, so if epsilon is 1, then you get the same here as before. And this is just the CSS version of what was a conductor's function before, while the rules are also like, if O goes towards 1, then this also goes towards taking log of the previous utility function. And we still have the same budget constraint. So now whenever you want to calculate utility for a given L and G, you calculate the same C, I bound them away from 0, and then I sort of write up all of this in code, very like straight ahead, just writing what's in all of these brackets and stuff like that. You of course need to be careful about that and sort of test it. Yeah, and then we said that questions 5 and 6 must be answered with the general formulation for 2 different sets of parameters. One is where sigma is close to 1 and rho is close to 1. And this will actually make the problem look like the previous problem in the limit. And the other where sort of we're further away from the conductor's case. And now we must find the G that solves G is equal to tau times W times L star of effective wage and government spending, which makes the problem a lot harder. So we need to, we're given a little hint. And this is just for a given tau. Given a little hint that we should first write code that solves the worker problem, given values of G and tau, and then find the correct G based on this. So this is actually what we've done here already, because now we just need to input the new this new function, which I've written up. So we can basically just call this for a given G, we can say gov dot L star numerical and now we want ufunc to be the CES version. And then we're just doing a numerical optimization of this function instead. So CES. I'll just call this L star. Yeah. All right, and then we get 14. That's not really, I mean, of course, it would make sense to sort of spend some time making sure that that looks reasonable. But it does, so we'll skip that part. Yes, so this solves the worker problem for given values in g and tau, but now we sort of have a root finding problem where we have g on both sides of the equation. Yeah, so we need to create a new function called, that's what we want to call this, CB. Yeah. Just to make sure sort of it's ordered, so this is only for conductors. And now here a new function for finding G in the CSS case. G find G. We'll give it a tau. And this is not, and this function needs to sort of compute the G that balances the budget in the CSS case. So the objective is not increasing U star, it's sort of, it's root finding this function. So it's going to be G minus part of tau times part of V times sol L star. And we set part of tau equals to the tau that we get here. So the function takes a specific tau. We also want to save this tau star because we need it in the next assignment. So you have to find using the tau found in question 4. This is not super important. Like if you hadn't been able to find tau in the previous assignment, then just use something like a half or something. Tau star C. Yeah. All right. Yeah. So for a given G, we want to calculate optimal labor supply. That was utility budget, usually this L star numerical. The given G with the CSS function. That gives us an L star for a given G and a given tau. And we can sort of see if we are any close. So we want this to be 0, so this equality holds. What's it called? Root scalar, yeah. And we don't know anything about G, I guess, except that it should be 0 or larger than 0. Don't know if and see if this works. Tau equals the tau star from before. Yeah, so it doesn't like the bounds. So I'll give it brackets. I guess what I'll do is, yeah, so I'll give it brackets and we sort of, if you're giving brackets without having a real sort of upper root, an upper bar, then you just have to sort of guess something that's way too high. And in this case, you sort of have that L can a max be 24? Yeah, so we can set that as the upper bar. At max, you can spend everything that could possibly be earned on government spending. And G should be 0. Yeah. Tau times W times 24. There are other ways to do this. Yeah. So bracket mine. Yeah. Okay. Now we found that G star is 3.65. And we can sort of test this by saying, just to make sure sort of everything works consistently, by saying if we want to calculate L star miracle of soft CS dot G star, then we should sort of get that it's stable still. Gov. So we calculate optimal labor supply for this G star, which should be stable, and then we calculate this function tau times part of W. We haven't defined par. Par. And then we calculate it with the optimal labor supply for the given tau. Sort dot L star. And then this should be the same because we should have found sort of a fixed point. Yeah, and it is. So that looks good. Okay, so now for a given tau, we can sort of find the fixed point of this equation, which is nice. Because in the last sub-question of this problem, we're asked to find the optimal tau given this sort of equation we have. So now we're basically just optimizing this function. Yeah. Oh no, we're not optimizing this function. We're optimizing the utility after calculating this function. Find tau star CS. Yeah, so this is not what you're supposed to do, but it gives us some things that we like. Yeah, so our new objective function is the utility, but not calculated like this. We have a given tau, then we call this function. To calculate that for the given tau, what should G be? Yes, so that find GCS for the new tau. We don't print it. And now we have both a G and the optimal L, so we can calculate utility. No, you so let's say yes for the L star and for the G star. And then we can just return the negative of the utility. Yeah. We can, yeah. Curve dot and our start sentence. And we find the exact same tau. And that's because we're in the case where the function very much acts like the cup doctors one. So these are the parameters currently used as the first set. And then you would also do this for the other exercise, but now I'll just do it for this one. So I create gov2 equals the gov model. And then I say par2 equals gov2 dot par, and then I set the other parameters. So that was these, right? That was sigma and rho. Yeah, sigma and rho. And then find tau star CSS. And this should be 2 as well. And I should call it. Yeah, and now we get a new tau star. If I was doing this for the exam, I would plot some of these functions to make sure they look logical. But now, in order to not make the video too long, I'll just check the solution to make sure everything makes sense. I'm not show you something that's wrong. So all of this is similar, and we get question 4. I get a slightly different optimal tax rate. All right, so after spending a lot of time trying to find out where I had made a mistake, I tried to rerun stuff from the beginning, and now it gives the correct answer. I think what might have happened is that at some point along, I might have changed the wages or some other parameter, and then not reset it. And then, of course, everything will be different. But the solution and sort of the approach was correct. Now I'll go forward to sort of relatively quickly going through the solution to the 2 next problems. This one. Yeah. Yeah. So I've done it a bit different in the upload solution. Yeah. So the next problem is sort of a model simulation problem. It's about labor adjustment costs, but it starts out with a static problem. You own a hair salon where you employ LT amount of hairdressers in each period to produce haircuts, and they have sort of a very direct production function where the amount of hairdressers you have, the more hair you cut. And of course, hairdressers can be half, can be a quarter hairdresser. The wage for each hairdresser is W. And that demand implies that you sort of have this price function. So that's this K demand shock, but otherwise sort of you get a higher price the less hairdressers you have. So the first people who want to get the hair cut will pay a very high price, but if you sort of want more people to come get the haircut, then you need to give them a lower price, and you give the same price to everybody. Yeah. And then you have a profit function, which is just like the price times how much haircuts you supply minus the wages you have to pay your hairdressers. And there are some baseline parameters. Again, we're asked to verify numerically an analytical solution that maximizes profits. How we do that is we write the model up in a Py class, sort of have all these are for later, we have all these parameters. And these are also for laters. And then we write up sort of all the functions that we're given here. So we have the price function, the static optimal L, so that's this one. And then we have the profits in the static version for a given L. And that's just this equation. Actually, it's this equation directly, but if you plot in the P, you get the other equation. And then we plot the profits, and it looks like this, which is basically just having a grid over all the different amount of labor you could employ, and then create a grid of the profits for these different labors, and then you plot it, and then you also show the analytical solution, and you can even calculate the numerical solution by optimizing. Now we get to sort of something a bit different. So you're asked to do it for different kappa shops. Yeah. Now we consider a dynamic version of the model, which means we're gonna have to simulate stuff. The demand shocks, the kappa sort of has this AR and logs thing. You don't have to worry too much about sort of where it comes from. Just sort of, you have a world where demand shocks changes each month. Sort of, you have a new demand shock, and they go by this structure where they're sort of correlated over time in some way. And you have a fixed adjustment cost if you want to hire or fire people. So if you want to make any changes to the amount of labor you employ, you sort of have to pay one cost, no matter how much you change it. And your future profits will be discounted. There's initial shock, and then you say you're looking at 10 years into the future, and each time period is a month, and you start out not employing anybody. So you have to pay the cost initially to employ people. And then we're given these sort of calculations for calculating the ex-post value of the salon. So like the profit discounted, all discounted future profits. Given that you know all the shops, this is very easy to count. But we sort of want an expected value, a prior expected value. And given that we have assumed this structure, we can create that prior expectation by simulating this one a lot of times and just calculating the average. For capital K many times. And then we want to have some sort of rule for how much labor we want to employ in each period to maximize H. We're given some values to baseline parameters, and they are also put in the initialization class. Okay. The first question, calculate the H, so this expected value of the discounted profits for the statically optimal L decision. And then you just have to choose K so the approximation is good enough to not affect your results substantially. This is more question of this is one of the questions where you have to talk a little bit and show that you sort of understand the idea of this. And the idea of this is just that sort of the larger K is, the more precise you calculate this expected value. And how do you sort of test for that? But the first issue is that you have to know how to calculate H. So we have to simulate all this. First, we just simulate the shocks. Simulate objects. We pre-allocate a bunch of arrays for each K times T. And then we draw the shocks. So the way I would do this is sort of, you have a bit of causal analysis from the very early economics in this. then you sort of have to think, okay, which variables are determined independently or sort of without the others, completely from parameters. And the first one is these epsilon shocks. You can sort of calculate them at the beginning without knowing anything else. Then you can calculate the kappas by looping forward in time. So we calculate the epsilon shocks by just drawing this normal distribution, and then we have the initial kappa, and then we can just loop forward using this equation and our drawn kappas. And you're doing this in log kappa, and then you can just take the exponent of it and get the kappa out. Yes, so that's the simulation of the shocks. If state is none, then it's sort of quasi-random, but you get out. But you can also set a state and say, I want this exact draw. And then we have to sort of evaluate this h function and this capital H function. The simplest way to do this is if it's not vectorized. So you just loop through all your capital K simulations. You initialize the initial amount of labor you supply, which is 0, and then you and then you set kappa to whatever the shock is, and then you use the rule. So in the first problem, the rule was that you should use the static solution. But there will be other rules, or set this function up in sort of a flexible way so we can have other rules. So I basically get this rule here from the get attribute function of self and the policy. So it picks static policy, which is it's actually lower. Static policy, but that's just using the static L optimal, which was a function defined up here. Yeah, which was just this function from the previous problem. So this one. This needs to go a bit faster, I think. So basically, you just do that in a loop, calculating the profits for each small k, so each simulation number, and for each t. And then every time you're done with all the time periods in one simulation, then you can calculate the small h for that simulation, so this number. And then you can calculate the big H once you're done with that. So don't look at this. This is just a smarter way of doing it. That's a bit faster. But you just calculate the mean of all the H, small h. And then you can print the results. So that's what happens here. But then there was this sub question about choosing a large enough K. So for this one, I chose K equals 10,000. But if you want to sort of check, okay, does the size of K matter a lot? Then you can sort of loop through different amounts of K. And you also want to have sort of multiple K number of simulations for each level of K you choose. Yeah, so you said for each K, you sort of calculate J number of simulations, so J number of capital H, and then I just print sort of what's the standard deviation, what's the minimum, and what's the maximum. And you can see if we only have 10 simulations, then we have sort of a pretty large range for what the expected discounted profits of this firm can be. While as K increases, then you sort of get smaller and smaller. Then it takes longer and longer time to run So it's okay to sort of have written this up and say, okay, we actually, if we put it to 100,000, then it takes 5 minutes to run, and we don't have time for that right now. But this is how we would do it, and then we would sort of stop at where it makes sense. And then it's okay to go down to 5,000 or something and say it's my computer is exploding because of all these numbers. I have to do it like this. That's totally fine. You just write it that you sort of, I think the optimal K would be this range, but I'm running it lower for now. Another thing is to sort of run it at the high number at the very end. Not at the very end, but sort of when you're done with the assignment, I've written in all the code correctly and have time to wait 5 minutes. It's just when you're writing the code, if something takes 5 minutes and you just have to make an adjustment, find an error, then it's going to take a lot, like 5 times 5 minutes to do something. Yeah, this is a plot you don't have to worry about. Yeah, no, we'll skip that. And now we're given a new policy that sort of asks you to set L star to the optimal static policy if it's far enough away from sort of what L is if you don't change it. And if it's not that far away, then you just don't change it. Yeah, and then I'll do this quite quickly. Yeah, just say you can use this same function now. The only thing that's changing is sort of what rule you're using. So we have a new function for the rule. I call this the delta policy, where you're just basically just implementing this function as a function of kappa and the lagged L. Yeah, that's all I'll say. That for a given delta, then you sort of calculate that expected discount profits kind of increases. In the next question, you're asked about finding the optimal delta, maximizing H. And something a little subtle you might not notice by just looking at this solution is that we're doing it for the same shock draw. So it's kind of important, not always super important, but sort of for being 100% correct, is that this evaluate function doesn't draw any new random numbers. It sticks with the random numbers it already has. So this evaluate sort of evaluates the probability for a different shock for a given shock draw, which is calculated in the simulate method. If I'd written it differently, so these shocks were drawn in the evaluate function, then this optimized steps would be much harder because you're sort of changing the goalposts a little bit each time you're drawing a new shock level. If your K is very large, then maybe it doesn't matter, but it could matter and does matter if your K is not that large. Because every time you're drawing a new shock, then the optimal delta will be slightly different. So basically, imagine in a world when K is small, then you can draw a lot of positive shocks in all of your simulations just by randomness. And then delta should maybe be higher or something. And you could also draw you can draw shocks with a lot more variance. And then maybe delta should be lower or something. And that's just why it's generally good to have one function where you draw random numbers and sort of other functions where you do other stuff, and making sure every time you're sort of optimizing over stuff that has a simulation, make sure you're not drawing new random numbers each time. And then you also get a nice smooth function, which you wouldn't if you were sort of drawing new random numbers each time. Skip this. And then you're asked to suggest an alternative policy. What's being tested here is sort of your understanding of everything you've done so far. Did you understand the model basically? And can you write new things in the model? It's not that important that the policy makes sense or anything. It's just important that it works within the scope of the model. So the added policy here is basically that two different ones. Find them. Alternative delta policy, where sort of the optimal L is allowed to be a bit different from the solution. So saying that you should adjust L star by something, making it a little bit lower or a little bit higher or something. I think what would make most sense would be to bring it closer to the mean. But that's not really the point. You suggest a new alternative policy, and then you sort of compare it with the probability of before. And you can see that doesn't really make any of the difference. This policy actually makes probability slightly lower in this simulation. Yeah, but it could be something else. It could be a new analytical result, maybe not that, but it could be sort of adjusting in a different way, or saying only adjust the medium of the different, or adjust maybe based on the medium, the mean of the previous shocks or something. Yeah. All right, the third problem. There's no paragraph for that there. All right, so the third problem is sort of an algorithmic problem. You're given this very nasty looking function, which has a global minimum at 0.0, but it also has a lot of local minimums. Yeah, and it's written up here for you. Yeah, and it's written in a way where it sort of takes a vector called x and gives in x1 and x2. So the version written here is basically where n is 2. Not make it too difficult to do. And then you're given the algorithm for a refined global optimizer with multi-start. So you're given an algorithm, you're given some parameters, then this smaller point, and you're asked to implement the refined global optimizer with multi-start and do some illustrations. Yeah. So the algorithm is choose some bounds for x. So this is the x vector, where we have x1 and x2, and a tolerance tau. We're actually given that here. So that's just part of the sort of the recipe. Then you choose the number of warm-up iterations, k underbar, and maximum number of iterations, k. Then at step 3, you say for each iteration for k from 0 to upper k, do this. Draw a new random set of k or of x1 and x2 uniformly within the chosen bounds. Then the next step says if k is smaller than k underbar, then you should immediately go to step E and then run the optimizer with x k0 as initial guess and x k star as result. This is sort of a bit ambiguous, but this k0 is actually this xk. So you're drawing a guess, and we'll see when we get later that sort of here you're adjusting the guess, but if we're jumping ahead, then you're just using the randomly drawn guess initially. And then you set x star to whatever you found as the optimum using your optimizer. If k0, or if it's better than your previous result. So basically, you know this function has a lot of local minimums. You're trying to find the global minimum. So what you're doing while k bar or k is less than k underbar is basically just that you're drawing random starting values, random initial guesses, calling the optimizers and trying to sort of find a local minimum given the guess. And then if this is the best minimum you found, you're saying this is the temporarily local minimum or the temporary global minimum or the best minimum I've found so far. And then if it's not small enough, you sort of know that the minimum is function value of 0. If it's not small enough, then you go to step 4. If it is small enough, you go to step 4. Otherwise, you go to another iteration. And if k gets larger than k underbar, then you're sort of just adjusting, you're calculating an adjustment factor. And this goes from, remember, I think it goes from a half to 1, basically. Yeah, but it goes as sort of it. It goes from 1 to a half, must be. So it's, you start up putting a lot of weight on your randomly drawn guess, and then as k increases, you put more and more weight on your previously found global minimum. So you're sort of moving the optimizer toward the lowest point you found so far. Yeah, and then you're doing the same steps as before. And if you sort of find something that's very close to 0, then you say, okay, I actually found the correct result. And the code follows these steps quite closely. So basically just writing up for k and k range k. So all these things. So the first steps are chosen, and then you go through the first steps, the bounds and tolerance and the warm-up iteration. That's all just options you put in. And then you go through this iteration of doing this. For k and range k, you draw uniformly guesses. If you're past the warm-up phase, then you adjust these guesses. If you're not, then you just use the guesses. And we want to store the guesses. We call the optimizer. If it's the best thing we found so far, then we save it. And we sort of initialize f star to be infinitely big. And we're minimizing. So if k is 0, we'll also update this because it's the first step. And if f star becomes sufficiently close to 0, then we break out the loop and return the result. Yes, and then there's a visualization of this, and you can sort of see that here you're guessing randomly, and then you're adjusting more and more towards the best guess you've found. This is a bit hard to see, but you can actually see already in the random guesses, you get something that's a bit close to 0. So you'll be adjusting towards that all the way, but you still have sort of random guesses everywhere. Yeah, until you finally adjust something that's actually 0. Yeah. And then there's another question about sort of where to set this k. If you set k to 100, then you have more random guesses initially before sort of converging. The trade-off here is that sort of having a lot of random guesses can allow you to come close to the true value very fast because you will randomly guess something that's close. But also sort of this updating process also helps you sort of narrow down on where you want to go. For this given, so we just called the same function as before, changing k warm-up to 100. For this given simulation, you can see that it actually takes a lot more iterations. But we want to test this more formally, and we want to make sure that we have the same draws for the two tests of k under bar. So we set the seed for each loop of k under bar. Yeah, find over, and then we just call the optimizer and loop, and we do it 10 times. So this is sort of, you could do this in a lot of different ways. You can maybe also spell it correctly. But basically what you want to do is you want to make sure you want to compare k u bar equals 10 and k u bar equals 100. You want to make sure those comparisons have the same initial seed, so you're drawing the same numbers. And you maybe want to do it more than 1 times. So here we're just doing it 10 times. You can do it more. But there is a relatively clear winner when you do that k equals 10 is actually a bit better in this case. And it happens for all of the iterations, it looks like, that you finish with fewer iterations. Yeah. Okay, that was all for this video. Thank you for watching.